Hi friends, this is the fifth lecture in the lecture series for the preparation of GATE in mechanical engineering. Today we will be dealing with a concept called convective thermal resistance. Convective thermal resistance, and also we will be dealing with heat transfer through composite objects. Okay. So let's go to the first topic, that is convective thermal resistance. Convective thermal resistance, and this is denoted by the letter RTH, convective. So we all know that the convective heat transfer rate or convective heat transfer is governed by Newton's law of cooling. So in this Newton's law of cooling, we all know that Q dot is equal to HA delta T, where Q dot is the heat transfer rate and this H is the convective heat transfer coefficient, and this A is the area of heat transfer, and this delta T is the temperature difference. Please go through my previous lectures to get a better understanding. So we can rewrite this equation as Q dot is equal to delta T by 1 by HA. So if we compare this equation with delta T by RTH, we can find that this RTH will be equal to 1 by HA, and this is simply called the convective thermal resistance, and this is denoted by RTH, convective. So that's it. Next we will be dealing with the second topic or second concept, which is called the heat transfer through composite objects. In this case we will be dealing with the steps that we have to be followed during the analysis of heat transfer through composite objects. So this composite objects is simply means number of either plane walls or hollow cylinders or hollow spheres. These are connected in parallel or in series combinations. Okay, so the steps that we have to be followed is explained as step number 1. Just determine the thermal resistance of each objects. Second one or second step, that is determine the equivalent thermal resistance. Okay, and this equivalent thermal resistance for series combination, we have to find this RTH equivalent as R1 plus R2 plus etc plus Rn. So for parallel combination, we have to determine this 1 by RTH equivalent is equal to 1 by R1 plus 1 by R2 plus etc plus 1 by RL. Okay, so after determining this equivalent thermal resistance, we have to determine the heat transfer rate, which is Q dot is equal to delta T overall by RTH equivalent. As an example, I will explain these 3 steps for the particular case of 3 plane walls that are connected in series. Okay, suppose this is the first one, this is the second one, and this is the third one. Here at this side we are having temperature T1, here we are having temperature T2, T3 and T4. And since these are connected in series, we are determining or we are analyzing this through thermal circuits like this. So here we will be having temperature T1, here T4, T3, T2, and this is R1, R2, and this is R3. So step 1, R1, R2, R3 is what? Step number 2, determine this RTH equivalent. Here in this plane walls are connected in series, we can determine this RTH equivalent is equal to R1 plus R2 plus R3. Then this step number 3, it is Q dot, which is heat transfer rate, which is delta T overall temperature difference by RTH equivalent, that is equivalent thermal resistance. This overall temperature difference is T1 minus T4 by RTH equivalent. RTH equivalent is determined from this step. Okay, so this is it. In a similar manner, we can write this Q dot is equal to UA delta T overall, and this is motivated from the Newton's law of cooling. And here this U is called, here this U is called the overall heat transfer coefficient, and A and delta T overall are having the same meaning as in the previous cases. That is, A is area and delta T overall is the overall temperature difference, and this can be written as delta T overall by 1 by UA. If we compare this equation with delta T overall divided by RTH equivalent, we can write this RTH equivalent is equal to 1 by UA, and we can also write this as QA is equal to 1 by RTH equivalent.